will those logic hazards carry over to the circuit of NAND gates or NOR gates? And will our changes, will our fixes that get rid of those logic hazards go away? The textbook actually doesn't address this. And I was curious about it, so I thought we'd explore that together. What do you say? Sound like fun? Good way to start your Monday? All right. So, let's try. Look at this go. All right. So, let's do this. Let's start from the very beginning with just a for the generalized midterm expansion. Let's say that f is a function of a, b, c, and d. Let's do it with the truth table first. It's going to be 4 variables, a, b, c, and d. 0, 1, 0, 1, 0, 1, 0, 0, 0, 1. I'll try to fit it all in one. 1, 1, 1, 0, 0, 0. It's going to get small. 0, 0, 1, 1, 0, 1, 0, 0. Oh, it's not going to work. 0, 0, 1, 1, 0, 1. Come on. 1, 1, 1, 0. And then at the bottom, 1, 1, 1, 1. That's hilarious. Okay. So there's our inputs, A, B, C, and D. Just go and label the rows. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. And then our function f is going to be 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 0, all the way down. It's been a long time since we started with the truth table. And from this, we want to find, or design, or realize, I guess I should say, f is a circuit of NOR gates which is free of logic hazards. All right. So, what's the first thing we need to do? What's that? Right on. What's the midterm expansion?
All the.
I mean, what is it for this example?
Oh, okay. T3.
F function A, B, C, and D, and is equal to, you want to do midterms or max terms? All right, it's equal to the sum of midterms. Which ones?
2, 3, 7, 8, 10, 12.
2, 3, 7, 8. 7, 8. What do we have? 10 and 12. All right, so there we go. There's F as a sum of midterms. What's the next step? Step 3.
K-map?
Yeah, we're going to put it in K-map. This is a 4 variable K-map, so that's what we'll set up. Big box. And let's see, cut it in half, quarter it, cut it in half, quarter it. We got F, we got A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0 on the top. On the left side, 0, 0, 0, 1, 1, 1, 1, 0 on this side, and then we're going to go ahead and populate it. So let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right. Now,
Did we miss 14?
what's that?
Did we miss 14?
Did we miss 14? Did we miss it where? Oh, it's a question.
Yes.
No. 13, 14, 15 are zeros on the truth table. And they're not in the expression. So no, I don't think so. What's next?
Group them up.
What do we group? What is the them that you group?
The ones.
The ones, you sure? What do the rest of you guys think? Why the zeros? Exactly, right? Because we're trying to get a circuit of NOR gates, which means we need to get what at the very end? We need an AND gate at the very end. To get an AND gate at the very end, we got to do what? With the KMAC. We got to group the zeros. Good. Okay. So, what groups of zeros can we make? Or rather, what is our minimum solution? What's that? Top four. About these guys? Yeah. All right, so that's going to give us what? A or C, right?
And then the middle four on the right corner.
Let's see that again.
Like the middle four on the right corner. I don't know if that's the case.
These guys? Yeah. All right, now that's going to get us what? Yeah, A is 1, and D is 1, so A prime or D prime. Yeah, I was running out of room. But it's 0. All right. What else?
Oh, the bottom.
The bottom 2? What's that going to get us?
B prime or C prime or D.
Good. B prime or C prime or D. B prime or C prime or D. All right. So we're done with the KMAC? He says no. She says yes.
Don't we still have to come to the logic
Yeah, we
deficiency,
still have to.
whatever things?
You're right, we're not quite done with the KMAC, but we're done getting our minimum product of sum solutions, right? All right. So that means we have, now we need to find our logic adders, right? So where are our logic hazards going to be?
Anytime the boxes are adjacent.
What's that?
Anytime the boxes are adjacent.
You bet. Where does that happen here?
A lot of different places.
Okay, well, what's one of them?
At 1. At like this left, like the bottom left of this box and the top right of that box. The bottom right of this box, the top left of that box.
So I have no idea what this box and that
Okay,
box is.
okay.
You know, I realized now, there was like a couple weeks ago where I had this like kick-ass day where you guys were just like saying the numbers, and it occurred to me it's because I had the numbers written down.
Savvy.
Yep.
Yeah.
Yeah.
So the, what is that, 1 and 9?
So that, this one.
Mhm.
Yeah,
Mhm.
and, no, 1 and 9, right on, yeah. You bet. So, there and there, which means we're gonna have, so what is that? That's 1, 0, our transition between 1, 0, 0, 1, and 0, 0, 0, 1. There's gonna be a hazard there. What else?
5, 13.
5 and 13. All right, those guys. That's going to be what? 0, 1, 0, 1. And 1, 1, 0, 1. Anything else? 14 and 15. Yeah, that's going to be 1, 1, 1, 1. And 1, 1, 1, 0.
And 4 and 6.
Would you say 4 and 6?
Yeah.
Yeah. Off the top, let's see, it's 1, 0, 1, 0, 0. And what, 0, 1, 1, 0. Is that all? Cool. Okay. So let's do this. Let's draw our original logic circuit, and then we'll just kind of pick one, and we'll timing diagram that one. Then we'll convert it to NOR gates, and then we'll sort of work through the timing diagram again to see if the logic hazard still exists. So we're going to try to cram, since it's 2-level, cram this logic circuit. Into corner here. Let's see. All right, we got 1, 2, 3. What? 3 OR gates. Copy and AND gate. So 1, 2, 3. AND gate. That gets us F. Let's call that gate 1, gate 2, gate 3. And the first one is A. Or C. Second one is A prime or D. Let's do it like this. Let's do A. D, not B. And finally with B prime, C prime, D prime. B prime, C prime, D. Alright, there we go. Cool. Any questions about the one there? So I guess the next question is, which one of these fellows do you want to do?
Which one, huh?
Which one do you want to do? What's up?
One more, one more.
Or hold on. What's that?
Do we only have to do one of them?
I mean, if you want to do more, we can do more. For the sake, I mean, what do you mean?
I would have thought we would have had to account for all the places we were in.
We do, but we only have like 30 minutes.
Ah, okay.
So we're just going to do one of them.
Okay.
Third one?
What's that?
Third one?
The third one, the one that takes D, that sets everything equal to 1. And we'll go, D goes from 1 to 0.
Yes, sir.
All right, cool. Let's do it. See what happens. All right. So let's see. So we're going to say that what A equals B equals C equals 1. And we're going to take D from 1 to 0. So it said everything at 1, and we'll bring D to 0, and we'll see what happens. All right. And for the sake of conversation, let's just say the proper delay is 10 nanoseconds for all the gates. Nanoseconds. We're gonna need this in the text, but we got it. All right, so let's do. And force down at bottom. And then I'm just gonna work our way up G3. G2. And don't forget these are the zeros and ones, 1, 0, 1. 1, 0, 1, and we're switching what? D? I'll probably give myself some more room here. Oh, okay. So, let's see. So D starts at 1. And let's go 1, 2, 3, 4, let's go 5 nanoseconds, or 50 nanoseconds. And we'll say D clicks over to 0 and stays at 0 forever. All right, so going from top to bottom, G1, is G1 affected at all by this? No. G1 is going to stay at 1 forever. A and C are always equal to 1. All right, G2, is G2 affected? What happens? Let's see. So if A is 1, that means there's a 0 here, right? All right, so there's a 1 there, which means there's a 0 there. Which means that initially G2 is at what? These guys are both at 1.
That's 0.
So G2 starts life at 0. So that's this. Let's take it at least to there. Now, how long does it take? Okay, so, well, first off, now D goes from 0 to 1, which means G2 is going to do what?
Go from 0 to 1.
20 seconds.
It's going to go from 0 to 1.
Yeah.
How long is it going to take?
20,
It's going to take 20 seconds. Why 20?
because it's after both gates.
Good, right, because there's two gates. There's the inverter and the OR gate in between. So it's going to take 20 seconds for G2 to go from 0, or 20 nanoseconds. For G2 to go from 0, and then it clicks to 1. And then it should stay at 1 forever again. Cool. All right, now G3. G3 is going to be what? It's going to start life
A 1.
as what? 0, 0, and 1, right? So it starts life as 1. Take these to there. And then what happens? D goes to 0, which means G3 does what?
Goes to 0.
3 also goes to 0. And how long does it take?
10
It
nanoseconds.
takes 10 nanoseconds to get there. 10 nanoseconds, it drops to 0 and stays there. All right, so F, the output of the AND gate. The beginning of the universe is what? So if this is, if we started at what? Did we start at 1, 1, 1?
No, 1, 0, 1.
1, 0, 1. So that means our F starts at 0. And let's see what happens. We have let's see. Okay, because now I think the logic hazard never occurs here. Okay, so this first place, we've got what? G1 is equal to 1, G2 is equal to 0, G1 is equal to 1, which means F should be equal to what? Should be equal to 0, right? And it stays that way forever. Let's see. And then it transitions here. Right? It goes to 0, which means it should stay at 0. That's odd, huh? What's happened? Our logic either never appears, right? It stays at 0 forever. Huh, okay. So what do you think the deal is here? It says there should be a logic hazard, but there isn't.
Oh, it's one of those rules you taught us, isn't it?
What's that?
One of those rules you told us about? Oh, maybe I'm tripping. Like static hazard or something?
Yeah. Right, so there should have been a static hazard there since there was a junction.
Yeah.
But it didn't happen. Well, there's something wrong. So I didn't bring that ahead of time. So those of you guys are just like waiting for me to like sort of let the clock run out and then rhetorically just give you the answer. I have no idea.
That's when we get to.
I was hoping we could figure it out together. All right, what do you think?
What do I think?
Yeah, what do you think?
I think you should look things up before class.
What was the fun in that? No, I intentionally didn't want to do that because, you know, like I said, I could have just canceled class because the other class needs to catch up. But I thought it'd be fun to kind of explore this question together.
Why does gate 3 change to 0 5 seconds after D does, but the delay is 10 seconds?
Sounds like you're reading a question. Why does G3 change to 0 5 seconds after D. It didn't. These ticks are, I mean, we didn't like label them, but these are 10-second ticks, so that's 60. That's 40, that's 70, so on and so forth. And it's in nanoseconds. Michael, answer your question? Oh, wait and see if he's back. Oh, he's typing. Oh, I know what you're getting at. Because I think the difference you're looking at is the difference between G2 and G3, right? Since on G2, D was hidden behind the NOT gate, it took twice as long. It took 20 nanoseconds for it to click over, whereas G3 only took 10. Yeah, okay. So here's the thing. What do you guys think? Rules say it should be.
Is it because multiple logic hazards can cancel each other out?
Ooh, it's an interesting concept. Maybe. Let's revisit that in a second. What about, what would happen if we lost the NOT gates here? You know, remember, by the rules of drawing our two-level circuits, we're supposed to ignore these and assume they're available. So maybe the logic hazard appears as a function of those guys. Let's take a look at that. So let's say that, oh no, I erased the answers. Control Z. What do we have here? We have what, A prime and D prime, and here we had
B prime,
B prime, C prime, and D, right?
Mm-hmm.
Alright, so just for fun, let's take a look back. So G1 wasn't affected. Alright, so G2 switched from, what do we say? It started at 0, right? Same things are going to happen. G2 is going to start at 0. And after 10 nanoseconds, it's going to go to 1. And it's going to stay there. G3 is going to start at 1. And after 10 nanoseconds, it's oh. Ah. And it stays at 0. Well,
Doesn't that not change anything? Isn't F always 0 still?
yeah, right. My was a little bit premature.
Yep.
So I say, well, this goes to 1, and this also goes to 0, which means it stays at 0. Is it possible to have false positive hazard indicators?
You would still have noise.
What's that?
You would have noise at what is that, 60 nanoseconds?
Well, I mean, there's the ambiguousness, right?
Yeah,
There's that business.
that wouldn't be as clean as you wanted it to.
Yeah, that might, so you might get the hazard there just by sheer virtue of like which one triggers first, right? Because in reality, they're not all going to be the same length, right? This one might, you know, go first, and this one might drag out for another couple nanoseconds, which we call the positive equal there. This should have come up in the thing by the book. Interesting. Okay. Well, shoot, it's gonna kind of derail.
Should we just try another one?
What else would I explode? Yeah, let's try another one. That's the spirit. I like that.
Could it be because
Yeah,
the time
that's what I'm
delay
talking
is equal?
Let's try another one.
And if there were different time delays for each gate, it might introduce a logic hazard?
Yes. Yeah, so if we tweak the time delays for each gate, that might do it. But we can't really like say like one OR gate has a different time delay than the other. I mean, if we wanted to, yeah, we could like shoehorn in a version of time delays that works for us, but it doesn't really do us any good. Let's take a look at another one then. Fun. Let me check my notes for, because I did write some notes. Right?
I think one of the reasons it didn't appear the first time is that it's an AND gate. If it was an OR gate, there would have been a logic hazard the first time, because there was one of them that was split, but because there was one that stayed the same and that was low, it kept the logic hazard from appearing in F.
Yeah, you're right. You know, as they say, if things were different, it would have turned out differently, right? What? All right. I don't know. Which one do you want to try now? In my defense, from the textbook sets us up, and it just stops here and says, yeah, these are the hazards, but does not go on to demonstrate them. I'm going to write an email to the authors. Say something's fishy here, man. Okay. So let's try another one. Which one did we try? We tried this one. And then we'll go first. Let's try this one. See if that works out for us. So that's going to be what? The transition from 0, 1, 0, 1 to 1, 1, 0, 1. This one. So we're going to say what? B and D are equal to 1. C is equal to 0, and A is going to go from 0 to 1. All right, so let's set it up. We've got B and D is 0, which means that that's going to be a 1, a 1, a 0, and a 0, and a 0. And we're switching A again. We're switching A from 0 to 1, which means we're going to start with 0 and 1. I'm going to give us some more room on the chalkboard. Let's say, all right, A is going to go. It's about 40 nanoseconds. Start at 0. It goes to 1, and then stays the same. Then G1 starts at 0, and then after 10 nanoseconds goes to 1. Yeah? All right, I am going to do these in groups of 5. Call that 45, 50, 55, 60. Otherwise, everything's just crammed into one little place. Okay. And then it goes to 1. All right. G2 starts at 1 and stays at 1. Yeah? And then G3, oh, it went in. No, it stays there. And G3
stays at 1.
Stays at 1.
the one with the A, B is prime.
What's that?
It, B is inverted.
Yeah, D is supposed to be 0.
G2 should not be the same the whole way.
Okay. So since D is prime, A is prime, oh, so that's 0, right? Yeah? Yes, right?
Yeah, B is 0. D is prime 0.
So that's 0. And A prime is 1. And then what's 0?
Yeah.
Okay. So D2 goes from 1 to 0 after it switches over. Yeah? Switch here.
Are we not plotting the time for the not gates?
No, we're not. No. I'm wondering. And F, of course, is going to do what? It's going to start at 0, right? Because it's got 1 and 1 and 0. And it's going to stay at 0. We may have to update our definition for what a hazard looks like on a timing diagram. What's that? Let's,
If you use the not for G2, we're going to extend the 1 longer and make all of them 1, so then F goes to 1 at for like 10 seconds.
oh man, I like that. So you're saying
G2, extend it for 10 more seconds.
G2 will drag out if we draw a logic gate for A1, is that right here?
Yeah.
Yeah. Nice. Okay. Which means it's going to take 20 nanoseconds for it to do its business. Yeah?
Mm-hmm.
So that's 65 to 70. We start at 50, so we're going to go to there. 52 will stay at 1 until that point. And then go up to 0. G3 is unaffected because it doesn't have A, so it always stays there. So here we have, look at that. So now we have F starts at what? Starts at 0 again because G1. It's going to stay there until we get to this point, where we do in fact have 1, 1, 1, which means it's going to take another 10 nanoseconds. And go to 1, and it's going to stay there until here, and now we have 1, 0, 1, so it's going to take 10 nanoseconds to get there, and it's going to drop over. And there, now we actually do have our, what type of hazard is this? It goes from 0 to 1 back to 0.
Oh, that's
Static 0.
It's a static 0, yeah. So static being where it wants to be, and then the hazard is, of course, that it jumps to the other place. And it only happens once, which makes it a static hazard. If it happens more than once, then it's a very dynamic hazard. Okay, so that one worked out. Why did the other one not work out? Maybe there is a sort of possibility for false positives. Maybe we drew it incorrectly. That's cool. I'm sorry, I want to revisit that last one. We got 5. Okay. go back to this one. Now let's put the gates back, yeah. A prime, B prime, B prime, C, D. And let's start from the top here. So it's going to be 1, 1, 1. I want to go back to this one. And we're going to change D from 1 to 0. So that's going to stay 1 and 1 and give us 1. That is going to be 1, 1. It's going to be 0 and 0. So that one's going to be 0. And then 1, 1. That's going to be 0 and 0 and 1. Which means that's going to be 1. Now we can already tell this isn't going to work out, right? Like if you go back and look at it again, you can sort of now hopefully kind of reason it out, right? Because the D is switching, the inverter's up here, there's no inverter down here, which means we know that this one is going to happen first. So we're going to go from 1 to 0 here before this one goes from 0 to 1. So the timing is sort of out of whack. And what were we looking at? We're looking at here. Yeah?
No.
No, we're looking at here. 1, 1, 1, 1, 1, 1, 0. Yeah, something about that does a job. What went the other one? We went 0. To 1, right? So we say everything's there. That's going to stay 1. We're going to make that 0, which makes that 1. Oh, maybe. Let's see. 1, 1 makes that 0. We're going to make that 0. Which makes that 0. Makes that 0, makes that 1. Okay, we figured it out. You want to see it?
The D is going to go to 1 before that one goes to
Yeah.
G2 goes to 0.
So let's see. So let's see. G1 stays the same, stays 1, nobody cares. And you say that this is D. G2 is going to switch from 1 to 0. It's going to take 20 nanoseconds to get there.
Wait, then we said we're going to start D
What's
at
up?
0. So we're in G2.
Wait, say it all the time?
We're in G2 start at 1. Because
Yeah.
I'm starting D at 0.
No, what I said? So D is 0. Makes that 1. Makes that 1. Yeah, it's going to start at 1. Until D goes to 1. Which makes that 0. Which makes that 0, which means it's going to toggle back to 0. But it's going to take 20 nanoseconds to get there. So it's not going to be until 60. And that clicks over. And then G3 is going to go to 1, which means G3 is going to click from 0 to 1. So it's going to start at 0. It's going to go to 1, but it's only going to take 10 nanoseconds to get there. Oh, that. Boom, boom. Goes to 1. It stays there. Which means that F on our AND gate starts at 0 until that moment in time, in which case 10 nanoseconds it clicks over to 1, which is right when this one goes back to 0. So 10 nanoseconds later, it puts back to 0. And that's 0, 1, 0. So what were we doing wrong the first time?
Switching it from.
We're looking in the wrong direction, right? So it matters which direction we look at it from, right? So the transition in one direction may not have the logic hazards. You got to take your turn around and look at it the other way. I was getting really worried. I was like, that's gonna be really weird if like we just said like this was a logic hazard and there wasn't a logic hazard there. You got to look at it from both directions there. Cool.
So does that mean if we're looking at the timing diagram, we would want to have it go from like 0 to 1 back to 0 so we can check both transitions for logic hazards?
Exactly, yeah, that's what it means. Cool. Well, I hope thank you guys for being good sports and going along with me on this sort of extra adventure. Hopefully we learned something. And then so on Wednesday, we'll start with something pretty much entirely new. Starting in chapter 9. So I'll see you guys then. Thank you.
Ooh. You know what we're doing? It's so amazing to do that.